Cool. I think we can begin. Thank you everybody for coming in. My name is Vittorio, and today we're going to talk about data-oriented design in C++. So, just a few things about myself first. This is my first NDC, so I'm very excited to be here. I'm also coming back from CPCon that last week was in the US, so I'm a bit jet-lagged. Please forgive me for any, mistake or anything like that. Currently, I'm working as an independent consultant, training a mentor for C++ specific purposes. I am available, so this is my website. You can check out what I do and what I offer. The past 10 years, I've been working at Bloomberg, both on high-end performance systems, including our own microservice infrastructure and our market data analytics team. And I've delivered technical training inside the company for modern C++, metaprogramming, multithreading, and many other topics. I'm involved with standardization. If you heard of this thing, state function ref, I am partially responsible for it. It will be in C++ 26, and you can ask me a question later if you are interested. And I'm also very passionate about open source and gaming. I am one of the team members of the SFML library, but I've also contributed to other open source libraries such as SDL. I have 2 published games on Steam that are also open source and written from scratch in C++, and I like virtual reality stuff. And finally, last but not least, I've also co-authored this book called Embracing Modern C++ Safely. I wrote it with my friends and colleagues John Lakos, Rosista Klemenskov, and Aliras Meredith. And it is like a reference for modern C++, covering all the features and their pros and the cons and how to best apply them in a large-scale code base. Enough about me. So what are we going to do today? Today, we're going to try to talk about this new mindset, data-oriented design, and we're going to see how thinking data first can change the way you design your system and you basically write code to solve a problem. We're going to have a little bit of a refresher on hardware. We're going to talk about modern CPUs and how memory works. We're going to do this sort of interactively. I'm going to show you a demo soon, and we're going to measure how changing the data layout of our types without changing the actual operations that we do on them ends up unlocking very, very big performance gains. And also, I don't want to focus just on the performance aspect. I know probably many of you are familiar with the idea of cache-friendly programming and stuff like that, but I also want to show you how your code can be much simpler if you also apply these ideas to the way you structure the code base as a whole. And lastly, I'm not a very dogmatic person. I'm not saying, hey, you should completely, get rid of OOP and abstractions are bad. I kind of want to find a balance, something in the middle. So I'm going to try to also point out where using good old style OOP and C++ abstractions can still help you achieve your goals without sacrificing performance. So I'm just going to jump straight into this live demo. There's going to be a little simulation that we're going to basically implement sort of like step by step. Let's see if everything works. And what we have here is sort of a particle simulation, but I want to make it a little bit more interesting. So we have all these rockets that are producing some particles. You can see some sparks and some smoke. And every single entity you see on the screen is something that is affected by physics, can be individually sort of like tracked with an ID or something like that, and can relate to other entities, and allows you to basically customize its behavior. So just to be a little bit more formal, we have this requirement that everything should move according to position, velocity, and acceleration. Everything should be customizable, so we have these effects, particles can have different types, and we also have this notion of an emitter, which is an entity that continuously produces particles. We have actors, so everything you see on the screen, including every single particle, is supposed to have its own identity. So for example, if we want to track a specific particle or a specific rocket, we should be able to do that. And then it should be extensible, so we should design it in such a way that adding new particle types, new actor types should be easy. And now to show you something interesting, I've also added this UI over here where we can change the amount of rockets we have on the screen and the way that we store them internally. So right now I'm using this OOP kind of layout that we're going to implement quite soon. And you can see that if I increase the number of rockets and the speed of the simulation, it quickly becomes pretty slow and, let's say, unplayable at normal frame rates. We get around 30 FPS. But if we keep the same exact logic and we switch to other memory layouts, you can see how much nicer and much more responsive it is. And we can play around with this. We can experiment with different layouts. We can also, create a lot of rockets and stress test the system. And this gives us an idea of how changing the way that we store data can actually affect performance in practice. So keep this in mind. It's going to be something that we're going to work towards. I'm going to go back to the presentation now. Let me there we go. And of course, it's a bit of a toy example, but I try to make it a little bit more interesting than just particles. We have this idea that you can relate entities. So we're going to explore also what it means to have relationships in DoD, which is a bit more realistic compared to just having particles. But I do feel that despite the application being simple, the lessons you learn here are applicable to real-world code. So let's implement this. And I think where most people begin is OOP, right? You're going to start thinking about, okay, we have these different things. We have the rocket, the emitter, and the particle. So they're all entities. We can start from an entity base class, and then we can derive an emitter, a rocket, and a particle from it. And then you're going to think about, okay, we're going to have multiple particle types, multiple emitter types, so we're going to derive from those as well, and we're going to have smoke and fire, particle, and emitter. So this fulfills all our requirements. It's quite nice, if you want to add a new kind of actor, you just derive from entity, and you have the scaffolding in place. If you want to add a new kind of particle, you just derive from both the emitter and the particle, and you're done. This seems nice. So let's implement it. I'm going to use struct here and try to keep things concise. Obviously, in a real application, you would consider using classes with private and public, invariants, and so on, but I'm going to try to keep it simple so that we can focus on the memory layout aspect of things. So we're going to have our base class. It's going to be a polymorphic base, so we're going to have a virtual destructor. In this case, we can default it. And then because each entity must be updated, so its state must change over time and must be drawn on the screen, we're going to provide two virtual member functions, update that takes a delta time, so the amount of time that has passed between frames. And this draw function here uses this thing from SFML, which is called a render target, which basically tells you where you're going to render the thing. This could be a window, a texture, but in our demo, it's just the window that we display on the screen. Lastly, every entity is affected by physics, so we're going to have this position, velocity, acceleration, 2D vectors. And just to make it clear, this is not a std vector, it's just a bidimensional mathematical vector containing two floats, x and y. So pretty simple so far. We can already start adding some code. Every entity will have the same sort of logic when updating. We just increase the position by the velocity and the velocity by acceleration, and we scale everything by the delta time so that we can actually control our simulation speed and also make it scale with the hardware that we're running the program on. And finally, this is probably the thing that's a bit more interesting. Because entities will need to create other entities or potentially query the state of other entities, for example, the rocket and the emitter will spawn new particles, we need a way of referring to, let's say, the world, the parent, where all these entities are stored. So that's why we have this reference here to the world, and we also have this Boolean here that tells the world when we are done. So when the world is ready to clean up these entities, reclaim its memory, and end up removing and destroying them from the state of the program. Okay, so this is our base class. Particle is going to be quite simple. We just derive from entity, and they're going to have a scale, opacity, and rotation, which can change over time, and we're going to capture this with these rates and changes. In the update member function, we can just override the base class. We can invoke it, so we get nice dry code. We basically avoid having to re-implement the same logic. And then we do the same sort of integration for these quantities. And then finally, we basically say that a particle is alive as long as it's visible. Because every particle is going to fade away in our demo, we can reclaim them. We can clean them up when the opacity reaches 0 eventually. Just to show you an example of a very, derived class, the smoke particle would just derive from particle. It is exactly the same. We only override the draw here, and we specify that we're going to draw using the smoke texture. And you could do the same for the fire particles or other kind of entities you want to add in the future. Now, the interesting bit is how do we actually end up storing and managing all this stuff? So we're going to have this world class, which I mentioned before is going to be like the parent class. And because entities are polymorphic and we have to store them somewhere, I'm going to use the std vectors, the unique pointer of entity. Now, those among you familiar with caches and, let's say, CPU, memory, bandwidth, and stuff like that, we already start thinking, okay, this is going to be slow, we're going to allocate every single entity. But I just want to get like a bit of an idea. How many people have written or seen code like this in practice? Quite a few people, okay. So this is going to be how we store things. Update is going to be very simple. We'll loop over the entities and call update. Draw, the same thing. We loop over and call draw. And then we're going to have a cleanup function at the very end where we call erasive, which is a relatively new function that given a container and a predicate, it will efficiently remove everything that matches the predicate from the container. So yeah, this approach is very simple. It's also very popular. You can find it in a lot of places, even AAA game engines or stuff like Unity, SFML. They all use inheritance-based approach like this one. Last few things. The emitter is going to be responsible for spawning particles. So we're going to have some floating point numbers here to keep track of how often we spawn particles. And then we're going to do this. We're going to have another pure virtual function called spawn particle that is supposed to be derived from the actual concrete emitter types. So in update, we will periodically call spawn particle, but then the real work is going to be done by something like the smoke emitter, which will override spawn particle and end up deciding how that particle should behave. Now here you will see that inside spawn particle, we're going to use make unique. So we're going to allocate this particle, we're going to set the data, and then we're going to push it back into the world. So this is where that reference comes into play. From within the update function of an entity, we might end up affecting the state of the world as a whole. Very last thing is going to be the rocket, and I want to show you this just to make it a bit more interesting. We're going to have the rocket have some associated emitters with it, in this case a smoke emitter and fire emitter, that will continuously get updated to match the position, velocity, and speed of the rocket. This is not strictly necessary. Like for this demo, we could have had the rocket just spawn the particles directly, but I felt like that real systems in practice have these sort of relationships. I want to make it a bit more realistic, more interesting. So we're going to rely on this relationship aspect to tie together some entities and add some more interesting behavior. Now, we're using pointers here, and the reason we can use pointers safely, or let's say sort of safely, we just talk about Rust, is that we are relying on the fact that these entities are heap allocated and they're going to have a stable address in memory. So even when the entities vector ends up reallocating because it needs to grow, the pointer to the actual emitters will still be valid. So this is something very common in this sort of OOP-based architectures. Cool. So let's see how this actually performs in practice. So this is a little bit of a benchmark that I've run. I run it on my desktop PC, which is a bit more powerful than the tablet. You can see here I have a Core i9, DDR5 RAM, and I use Clang++ with O3 enabled. And I disable rendering. I just wanted to focus mostly on the update part, so how the actual CPU and memory end up working. But I'm going to tell you a little bit about rendering later in the talk. And we can see that with 200,000 entities, we have 2.3 milliseconds, double that amount, 6.6, 600K entities, 12 milliseconds, 800K 16.6, and 1 million entities 21.6. Now you may think these are milliseconds, they are relatively reasonable times, but it's not really the case, because if you think about a target which is very common for real-time applications, which could be 60 frames per second, the budget that you have to reach that target is 16.67 milliseconds per frame. So already with 600K entities, we're using most of our budgets just for the update. We are not even rendering them. So imagine either rendering on top or having more complicated calculations or more complicated systems. It would be pretty easy to reach that budget quite quickly. I also think that in 2025, 60 FPS is honestly pretty pathetic. Even mobile phones nowadays reach 120 FPS in most cases. They have nice refresh rates, feel more responsive, much more playable. So I think the step forward is 144 FPS, which is very common also in PC gaming and console gaming. And that is roughly 7 milliseconds per frame. So the budget is very, very small if you want to reach a very playable and nice feeling frame rate. So we're already basically blowing it just with 400K entities. And we're talking about C++, not Python. We should be able to process many, many entities at a time without really worrying about this sort of overheads. You've seen in the demo that when we change the memory layout, it gets much faster. So the problem is not actually in the algorithm or the operations that we're doing. The problem is in how we're storing the data. So we're going to have a little quick refresher on how memory works, and I'm going to give you a very high-level overview just to understand what the problem here might be. Cool. So at a very high level of abstraction, you can think of the CPU and the RAM as communicating through a bus. Of course, this is very high level. So if we peel one layer of the onion, you will see that we can also have another layer of abstraction that looks like this. Again, very far from what happens in reality, but at least it introduces this in this concept of a cache, which is really important to understand why the performance was so poor with OOP. Now, the reality is that any sort of data that you want to either read from RAM or write to RAM has to go through the memory hierarchy. In this case, I'm just showing you one cache. In reality, there are more levels, but everything has to go through the hierarchy. So if you want to read something from RAM, it first has to go through the cache, and then it can be processed by the CPU, and it can do the other way around as well. The cache is a very small but fast, let's say, buffer of memory that you end up having in your CPU. And you can think of it as a collection of these things that are called cache lines. And this idea of a cache line is really important because it's the smallest transferable unit of memory. Even if you care about an individual byte somewhere in memory, you still have to take the entire cache line where that byte resides in order to do anything with it, which means that if the data next to that byte is not meaningful, you're just grabbing data for no reason that is not useful to you. Just to make it clear, you can also imagine the RAM being a huge collection of cache lines, much, much bigger than the cache. We're talking about order of gigabytes here, and order of kilobytes there for the L1 cache. And if you want to get something from RAM, you have to take the entire cache line with you. So just to give you an idea, let's say we care about the data at address 18. We will see that that data is not in cache, the cache is empty, which means we have to go to the RAM, and we can find it over there. That's the address 18. Now, even again, if we only care about that address in particular, you are forced to consider the entire cache line. So you're going to take the whole thing, which is called a cache miss, because we're fetching the entire cache line from the RAM, and we are going to copy it into our cache over here. And again, if we don't care about that A, B, and C, and E, the data that we just fetched from RAM is completely useless, and it just happened to be there in proximity of D. In the best case scenario instead, let's say we want to read address 19, for example, we have it in the cache already. We happen to take it while we were reading address 18, so we can identify it there. And because it's already in cache, we don't need to go to the RAM. This is called a cache hit, and we are able to immediately read the data over there without having the round trip. So this is something that is important to avoid these potentially expensive trips on the bus between the memory hierarchy. So why am I telling you this? How much does it actually matter in practice? And I like to show you this visually. We're going to do a little bit of a race. We're going to have L1 cache and CPU at the top, and we're going to have RAM and CPU at the bottom, and we're going to see how long a piece of data takes to perform a round trip between cache and CPU or RAM and CPU. So 3, 2, 1. So this slide is severely slowed down because these things happen at the order of nanoseconds, but it is to scale. So by the time that the cache has done multiple round trips with the CPU core, RAM hasn't even done a single way forward. So it is much, much slower, and this actually can dominate the performance overhead of a program. In short, we can say that on modern hardware, the round-trip latency for RAM is around 70 times or 100 times slower than the round-trip latency for L1 cache, which is pretty significant. And just to give you some more ideas, the average time that a human blink takes is around 100 milliseconds, which means that every single time that you blink, you will have 200 million round trips with cache. So you have a lot of time to do things if your data is stored in cache, and much less time if it's stored in RAM and needs to be fetched every single time. So the point I'm trying to make is, many times the performance of a program is dominated by the way that the data is stored, the proximity memory, and not by the choice of algorithm or data structures. This is very important on modern hardware. So what have we learned so far? Super important, the smallest unit of transferable memory is called a cache line. Again, if you only care about 1 byte, you still have to take the whole thing. And typically, it is around 64 bytes on modern hardware, but it depends on your CPU. All data must always traverse the memory hierarchy. So, and we mentioned this, it can be 100 times slower between a 1 cache and RAM. So you have to think about going through all the levels of cache before you can actually do something with the data. It's best if the data is already in cache. So if you design your program so that the data that is already stays together, then you will minimize the amount of memory churn that needs to happen between the cache and the CPU. So the spatial locality of data greatly affects performance, as I mentioned before, even more than big O notation and stuff like that. It's really important that you store data in the right place. So we can already think about some tips, some advice, and I would probably say that if you have data that is supposed to be used together, so related data, you should store it together in memory. And this means, in practice, prefer using flat and contiguous storage rather than something which is node-based or dynamic allocations. The other thing that I didn't mention, but it's also really important, is using predictable patterns to access data. CPUs have something called prefetching, which is a speculative algorithm that tries to figure out, let's say, what the possible next useful piece of data is going to be by looking at the patterns of access that you have. For example, if you are iterating over a container forwards or backwards or in threaded accesses, the CPU can sort of like predict that, and it can start taking the cache lines that you might need according to that pattern even before you request them. So if your access pattern is predictable, then you're going to likely get that data already in cache even before you wanted it explicitly, which makes it very, very efficient to iterate over things that are stored in a predictable way. Now, I basically lied to you. The reality is much more complex. It's something like this. You have multiple levels of cache. Of course, L3 is going to be bigger but slower, L2 a bit faster, a bit smaller, and L1 is the smallest but fastest, and it's also divided in data and instructions. But I don't want to make this a talk about how cache works and all that stuff. There's plenty of good talks about that already, and I would point you to this talk by Scott Myers back in 2014, which is still very relevant today. Also, as CPPCon, I saw a talk from Jonathan Mueller, which was called Cache-Friendly C++, that also covers some other topics. And I feel like if you see this one and Jonathan's talk, you're going to have a very good and deep understanding of everything that surrounds the idea of cache and memory. Cool. So given that, why was our implementation slow? What are we doing that is expensive? And I feel like we can sort of like just look at the world here, and by looking at what we're doing, we can get the full picture of why this code is so inefficient on modern hardware. Quite obviously, this is the first culprit. We are storing a vector of unique pointer of entity. Unique pointer is a heap allocation, and they're all individually allocating different entities. There is no guarantee that the allocator is going to be nice and put them close to each other, so this is likely going to be all scattered around in memory. Also, as you create and destroy this, the memory will also keep diffusing over and over again, so there is no guarantee this will be contiguous at any point in time. Which means, in the worst case scenario, as you're iterating over the entities here, here, and in arrays if, you might have a cache miss per iteration, which is probably the worst thing you can do for modern CPU hardware, which basically means you have to go to the RAM or to a higher level of cache every time you iterate through these containers. There's also other source of overhead. Here we have some virtual dispatch when we're calling update and draw. We are, looking at the vtable, figuring out which one we should call in practice, which is probably not as significant as the cache miss, but still a source of performance loss. And if you look at the way we create and destroy entities, we have frequent dynamic allocation here and frequent dynamic deallocation. And again, because we have to go through the allocator and needs to keep track of the heap and link everything together, this is going to be another source of overhead. So yeah, and I mentioned before, this code, I see it all the time, even in very new architectures. You can still ship very successful software doing something like this, but if you care about maximizing your efficiency and if you have requirements on your performance, this is likely not going to help you meet those. So why did we write our code this way? And I feel like most people, especially when they learn programming in universities or books or whatever, they really are their first approach is the object-oriented mindset. That's what they learn about. They learn about classes, polymorphism, and so on. So it comes quite natural to think of code in this way. It's also, I think, a human choice in the sense that it aligns with the way we represent the world. We think about entities as individuals, and then we try to represent that in the code that we are writing. So what is this object-oriented mindset? As I mentioned, we try to model a world of autonomous objects. We think of objects as self-contained agents that have their own identity responsibilities, and we try to encapsulate everything into that idea. The things that we have in our code, they communicate through messages. In the example that we had with the rockets, is the main loop that asks the entities, please update yourself, please draw yourself. So the higher level doesn't really have visibility of what's happening, it's merely communicating, asking those entities to do something. OP tends to hide data and expose behavior. You know, we have private, we store all our data in the private section. We don't want to make it visible. We want to give ourselves the chance in the future to change the internal representation without changing how it is actually used. So the world doesn't really care how a particle gets updated, only that it does, and it gives us this, let's say, barrier where we can then in the future change what happens under the hood. And also I feel like OP tends to encourage people to plan for the unknown. You try to think about an abstraction, an interface that will work in the future. You might extend for any purpose you haven't predicted. But I chose the word bet very carefully here because it is a bet. It's really hard to predict how requirements change. It's really hard to predict what you might need. And if you end up choosing the wrong abstraction at the beginning, you will pay for it later. Many times it's better to not go through that process of trying to abstract and trying to find a system that works for the future, but just do the simple thing and then update it when needed. So in contrast to this mindset, there is this idea of the data-oriented mindset. And this is very different. It's the antithesis of OP, but one of the claims that I'm going to try to prove later is that they can live together, they can coexist. But right now let's focus on this idea of DoD. So when you talk about data-oriented code bases, you don't try to model individual objects, but you try to model a world of data transformation. You sort of think of code as a pipeline that just transforms data from one state to the other, and that is your focus. It's not the individual object, it's the transformation as a whole. What that means is that you're not going to have messages between individual things, but you're going to directly operate on batches of data. The main loop, the world in this case, will be in control. It will be directly manipulating the data in bulk. This is important because once you have, a particle, an entity on a rocket, you usually have more than one. So why are we focusing on designing our code for the special case, for the individual, or in reality the common case that we have many of them? And CPUs and hardware likes to process things in bulk, so that also ends up leveraging the power of modern computers. We don't want to hide data. Data is the most important thing. We want to make it visible, we want to expose it. And we don't want to hide the behavior into classes. We want to bring it one level higher up and centralize it so that we can process things in bulk in a way that's transparent and not hidden. And this allows us to also decide to lay out the data according to the access patterns we're going to have to process it, which means we can figure out how to best lay it out to minimize cache misses. And finally, this is more philosophical, but I feel like DoD mindset is more pragmatic. It tends to encourage people to plan for today. So you have a problem right now. What you're going to do is try to solve that problem, not try to solve problems you might have in the future, prioritize performance and simplicity. And ironically, most of the times doing this ends up being easier to change in the future compared to having chosen the wrong abstraction and try to fit everything into that. So this might actually also help you be more flexible later on. So how do we shift our mindset? I feel like the first thing you have to sort of accept is that the only purpose of code is to transform data. It's a tool for data transformation. So your focus should be on the data itself, not on trying to model this nice view of the world into code. It can be fun sometimes to try and abstract away things, but what really provides value is the data and how it's transformed. Which means that the data is the centerpiece. It's not something that you want to hide, it's something that you want to make visible. You want to understand the shape of the data you have, the size, the access patterns, and based on those things that you want to implement your framework. Computers, even very modern ones, they still thrive on very simple and predictable work. So trying to feed them long and straight runs of data ends up having the best sort of results. In general, what I want to say is basically design for the machine that you have, not the metaphor that you have in your head. Because a solution which is effective is aligned with the physical reality of the hardware, not with your own view of the world. Cool. Just going to take a sip here. So let's start doing this. Let's start optimizing your code according to these principles. We're going to do a few things for our first optimization pass. First of all, we're going to get rid of heap allocations. That was probably the biggest source of overhead. We're going to flatten the hierarchy, no more inheritance whatsoever. We're going to decouple the data from logic so that the entities are just the data and the world is the one responsible for dealing with the behavior. And finally, if you remember, we had this vector of entity, but now we're going to have different types. So the way we're going to do this is just have more vectors. We're going to have a vector for rockets, vector for particles, and so on. So from one polymorphic vector, we're going to have many concrete ones. This is a very common transformation that happens when you apply DoD in your code. Okay, so just to show you what we're going to have our emitter, our particle, and our rocket. They are all going to have the same physics data, so we have a little bit of repetition, but not a big deal. You know, if we had more than that, we could consider non-polymorphic inheritance or mix-ins, but this works for our use case. The emitter is still going to have its own data, the particle is still going to have its own data, but now we have a problem, right? Before, we could distinguish between the smoke and fire particles because we had two different types. So how do we do that now? Well, for this particular optimization, we're going to do something very simple. We're just going to have an enum class that tells us whether the particle is of smoke type or fire type, and we're going to store this in our structs. It's not the best. I'm going to show you an improvement later, but it's going to be good enough for a first step. The other problem is that in Rocket before, we were relating to some emitters by using pointers. But now that we're not heap allocating things individually anymore, we don't have that address stability guarantee that we had before. So what do we do now? Well, commonly in this sort of systems, you use handles or indices. In this case, what I'm going to do is I'm going to slightly change the way I store emitters so that they're going to be stable in terms of indices, but not necessarily memory. And then to relate rockets to emitters, I'm just going to use the size t, so just the index of those emitters in the container. There are many ways you can do this, but generally speaking, when you work with data-oriented design, you think of relationships in a similar way that you do with databases. You're going to use indices, IDs, stuff that is real data to relate things together. Okay, so let's see how the world changes. We're going to have a vector of particle, very flat and contiguous storage for our particles. We're going to have a vector of rockets and an associated add rocket function that ends up doing the wiring between the rockets and the emitters. And then we're going to do this for our emitters, which is quite interesting. Because we want to guarantee index stability, I'm going to have a vector of optional of emitters so that the same slot is always going to refer to the same emitter. If I want to destroy it, I can just clear the optional and then put something back in. But even as the vector reallocates or as I destroy things, the identity of this entity is going to be maintained as they're not going to move around in the vector. To help, put everything together, we're going to have this add emitter function, which, given an emitter, will put it in the first free spot available in the vector and return the index where that emitter was used. And if you look at the bottom left, basically those indices will be initialized by what add emitter returns in order to tie everything together and end up having proper relationships. As I mentioned before, you can do many better things than this. You could use a custom handle type, add some extra safety onto it, but this is going to be good enough just to show the idea behind these relationships in DoD. So how do we actually update things? Well, now the world is responsible, and we can see everything that is done through the update member function over here. We're going to loop over all the particles and then perform our integration all in one place, which is quite nice. Then for the emitters, we're going to loop over all the emitters, skip the ones that are empty, those are the slots that we might want to fill in later, perform our basic operations just like before, and then we're going to do this. Again, we're going to see how this changes later, but right now we're going to basically say, if I need to spawn a particle, I'm going to check the type of emitter that I am, and if I'm a smoke particle, I'm going to push back a particle with that data. If I'm a fire particle, I'm going to push back a particle with that data. So we have some branching here in a loop that might be problematic, but we're going to see later how we can avoid this and how we can simplify it even further. And finally, for the rockets, again, the basic stuff is going to be there. And then to communicate with the associated emitters, we can just use the index that we had before. We're going to find the corresponding emitter in the vector, check if it has a value. In this case, I think we could assert it. It should be something that is always true for this particular design. And then once we get the actual emitter, we can change its position, for example, to be the same position as the rocket, offset a little bit so that it actually looks better on the screen. And we can do the same for the fire emitter. So here, we're using the index, and we are directly finding what we need in the emitter's vectors as a way of relating entities together. Now, how do we deal with the emitter's slots? So this is probably the most naive algorithm. I'm just going to loop through all the slots. If there is an empty one, I'm going to put the emitter in there and return the index. Otherwise, I'm going to call emplaceback, create a new slot, and return the last index. This is a linear complexity algorithm, not very clever, but because the number of emitters is very small compared to the number of particles, this doesn't matter. In a real program, if you had this being done in a hot part of your program, what you could do is you could store an extra vector with all the indices of the free slots and just pop from the vector, fill the slot, and then reclaim that index when you're done. So you could turn this from a linear algorithm into a constant time algorithm by having this extra storage for the indices. But this works fine for our purposes in our demo. Finally, the last piece is the cleanup. Here is going to be done in phases. First, we're going to clean up all the particles. And then for the rockets, we're going to also do the same. We're going to check if we're out of bounds on the right-hand side of the screen. And if we are out of bounds, we can take this opportunity also to reset the corresponding emitters and then return true. So the deletion of the rockets and emitters, because they are closely related, is going to be done together in the same function here, depending on the condition that the rockets are out of bounds. So we have multiple, again, passes over the data. Okay, so now that we have this, how does the performance actually change? Well, this is what we had before, and I think it's going to be very clear that the performance is significantly improved. On average, we have a 70% decrease in update time, which frees up a lot of budget for other things, and you can see it before in the demo, is actually noticeable when you run the application. You feel it's much more responsive and smooth. So this is very nice. The other thing that I'm not showing here is that the rendering performance as well improved by roughly 8 times, because now that the data is laid out by group, by type, it was much easier to sort of like prepare it for the GPU. GPUs are heavily parallel. They really like when data is laid out contiguously. So you will see that there is a parallel between data-oriented design and GPU programming. If you store your data in a way that's good for the CPU, it's going to end up also being easier to send it to the GPU in the right way to render it efficiently. So in this case, I managed to use instance drawing, which wasn't really easy before with the OOP approach. Okay, so we can see that the performance changes, but I wanted to say at the beginning of the talk that this is not just going to be about performance. I also want to talk about simplicity. So I'm going to show you how some things that are hard in OOP become quite easy with this design. And I'm going to start with something real. For the demo, I actually wanted to keep track not only of the total number of entities, but specifically the number of rockets that were on the screen. And I thought this would be easier, right? Just have a counter on the screen. But with the OOP approach, it was harder than I expected. So my first thought was, okay, this is a special case. I just want to have a counter. So this is the perfect use for dynamic cast. It's a one-off thing. I just want to count the number of rockets, so I'm just going to do this in the OOP design. Turns out that it is actually too slow. This ends up showing up on my profiler and taking several milliseconds, just for a counter on the screen. So don't really want to sacrifice performance that much. I'm not going to do that. So then I thought, okay, what if I have the entity base class expose its own type, so I can do the same thing, but avoid the overhead of dynamic cast? And again, I've seen this in practice, but this is bad. This defeats the purpose of OOP. I want to think of an entity as an entity. I don't want to know what the entity actually is. I want to be able to use the list code substitution principle. I don't want to have the entity to report that it is a rocket. Just doesn't make sense to use OOP in that way. Then I thought about, okay, maybe when I create the rocket, I can have the world register that. So I'm going to add some side effects in the constructor and the structure of the rocket. Don't like that. It's more state, more mutation that happens somewhere deeper in the program. And I also feel like we're violating the single responsibility principle. Why is the rocket responsible for counting the number of rockets? It doesn't really make sense. And lastly, I tried, okay, maybe I can do something like this. In the world, I can have an add rocket that keeps track of the number of rockets. And then when I clean up, I'm going to decrement that. But again, it just doesn't feel right. It's a specialized function for rockets. And the purpose of OOP is that we don't want to think about the derived types. We want to use the base class and forget about what the derived type is. And this also adds more complexity because we have to do all this bookkeeping inside the world. So yeah, I couldn't do this. I couldn't count the number of rockets in a way that was satisfying in OOP. But with the DoD approach that we just seen, that's it. We already have the number of rockets. I'm just going to ask for the size of the rockets vector, and that's it. We get them for free. So many things that ends up being complicated in OOP end up being simpler because you already have the data laid out in this sort of patterns. You already have the data laid out by group and in such a way that you can query properties of the data much more easily. Other example here, let's say we want to have a bit of a code review. Maybe we are a new person coming on a team that's working on this demo, and we want to try to understand how this demo works. In the OOP approach, we're immediately going to see this, which should be a bit of an alarm bell. We see that every entity has a reference to the world and this extra state, which means that any derived class might do something in its update which might affect the state of the world. So now to have a full picture of what's going on, we have to look at every single derived class, see what it does in the update, and try to keep track of that across multiple source files. It's really not easy, especially if the number of entities scales. The other thing I'm not a fan of is that because we have the draw member function in the interface, we have a very tight coupling with the rendering system. So if we want to change the library, maybe from SFML to something else, we're going to have to change every single class that it's using it. And that's not going to happen, right? We're just going to say, okay, we chose this at the beginning, we're going to use that. So it kind of like locks us in, it kind of like fossilizes the program into that library, which is something that I don't really like. At the same time, if you look at the world, you cannot really make any assumptions. That could do anything. Might be a particle update, might end up destroying something, might end up creating something. So it's a bit hard to reason about this program as a whole if you don't have a full picture of everything that's going on. And yeah, we've seen this. If you create particles, it will affect the world from within a very deep layer of the hierarchy. In contrast, I feel like if you look at the DoD approach, first of all, the entities are just data. So there are no virtual member function, there is no behavior, no logic. What you see is what you get is just plain old data, very simple, very straightforward to think about. If you look at the world, you immediately know everything that can happen in this program. You're going to have emitters, particles, and rockets. Nothing more, nothing less. The data is not hidden, it's clearly visible there. And if you know what happens every frame, again, you just have to look in one place, the update function in world. It's going to have a stage-based approach where we first do everything with the entities, then the emitters, then the rockets. So again, it's quite simple. All the logic is here. And any sort of relationship that you might have between entities is going to be here as well. You don't have to jump around in source code to figure out where things are. Draw it the same thing. You will see that we still have some coupling with the rendering system, but now it's one function, not n functions. So it's much looser than before. And now it becomes a realistic idea to actually change this to use some other library because we don't have to go through all the classes. We just have one place where we perform the draw, and that's going to be much easier to change compared to the entirety of the program. At the same it also feels like that using DoD opens up new opportunities. So, for example, think about the requirement of having to serialize the state of the program. I want to be able to serialize my program and potentially load it and save it at will. With the OOP approach, you might do something like this. I've actually seen this done in practice. You will have a virtual member function called serialize and deserialize for the entity. You will implement that in the derived types and everything is fine. However, I don't think it's fine. First of all, this is very tight coupling. You are basically saying that you want to use IO streams and you're going to have to decide on a format right here and now. You won't be able to decide, hey, I want to change this to JSON, XML. As soon as you define it, because it's going to be part of your hierarchy, it's going to be something that you're locked in. I also deeply care about compilation time. I've done a few talks on that as well. And IOStream is a particularly, let's say, expensive header to include. So once you actually have it in your base class, it's going to be virally included in every translation unit that includes the entity, which means you're also going to slow down your compilation times. And again, it just doesn't feel right. I want to have a translation unit which is dedicated to serialization. Why should the serialization stuff be spread all across my program? So one of the ways that you can solve this with OOP is using a pattern, like the visitor pattern. So what you could do is have a visitor struct, you define your visit member functions for all the types, and then your entity will accept a visitor. Now you are decoupling this idea of serialization from the entity itself. You're adding this extra layer to sort of like do whatever you want. And then what you can do is you can define a serialization visitor, you can store the O stream in there, override all that stuff, and it's great, right? Until you realize, again, we're defeating the purpose of OOP because we are listing all the types explicitly. We are losing that ability of saying, hey, type is responsible for itself. We now are recentralizing the data in the visitor, which seems a bit it seems a bit against the principle, the spirit of OOP. At the same time, we're adding even more overhead because we have double dispatch now, and we have to manually keep in sync serialization visitor with the base class and potentially a deserialization visitor. Another thing that bugs me is that something that should be a function parameter, DO stream, should only be accessible for the duration of the serialization call, now becomes state. So we have to use a member variable for something that conceptually could just be a function parameter. You can work around this and so on. Then you also realize, hey, we were relying on pointers before. So what do we do now? How do we serialize this? It's not impossible, but now you have to think about a mapping between a pointer to something that can go on the disk. And when you deserialize, you have to sort of map it and link them together. It's a pain. If you've done it, you know what I'm talking about. But this is not easy to serialize. And my point is, does it really have to be so complicated? I just want to write stuff to the disk and then load it again. And the main problem is that the OOP sort of design drives you into this mess of patterns and pointers and so on. So it does become complicated because of that. Now, if you look at the DoD approach, it's just a simple function. I'm going to have a function called serialize. It takes the world by const reference, my stream as a parameter, and then within the body, I can loop over all the data, do whatever I want to do. It could be JSON, XML, whatever, and that's it. It's a single function. Of course, you could, refactor this to have inner functions for the rocket, particles, and emitters. But my point is there is one place that is centralized where I perform serialization, one translation unit where I might need to include IOStream, and it's just data. The relationships are just indices, so I can serialize and deserialize at will. I don't need to do any mapping between pointers and data on the disk. So I talked about opportunities at the beginning. What am I talking about? Well, once you do this, you sort of realize that the entire state of the program is just data. You don't have anything which is hardware specific or session specific. You don't have addresses, pointers. So avoiding that allows you to implement trivial state loading and saving, which is not only useful as a requirement, but it can help you test, debug, and have tooling. If you can replay the state of your program from any sort of save point, you can create a test with some interesting case, save it, and replay it from there. If you have a weird bug, you can save the state and try it again as many times as you want. And also, you've seen this with game engines usually, if the state of the program is data, it's really easy to write a UI for it or a tool that helps you understand what's going on or even interact with it in real time as you are working on the game or application. Networking also becomes way easier. It's just data. So if you want to have multiplayer simulation, you can send a snapshot of the entire state as somebody joins in. And once they joined your server or whatever, you can keep sending updates as deltas that you would apply on top of the state. And again, if you had to do this with the pointer-based approach, it becomes hard to synchronize relationships and things like that between the network if you're using pointers and relation addressability. Good? Okay. Lastly, I want to show you multithreading. Should make the point. Should have made the point already, but in OOP, this can do anything. How do you even begin multithreading it? Maybe you just want to multithread the particles. You could extract the particles by dynamic casting, store them somewhere, do the multithread, and then re-put the data in there. I don't know where to begin. It's not easy. You have the problem that you're creating new entities during updates, so you have side effects. Definitely not trivially parallelizable. You can probably figure out a way of doing so, but it's not as easy as saying, okay, I'm going to just run the loop in multiple chunks because you have side effects and entities that interact with each other. So not very easy. With the DoD approach, this is the definition of trivially parallelizable. You can literally chunk this vertically, horizontally. I even just included OpenMP and just add a pragma OpenMP parallel 4, and it does it for me, and I don't have to worry about anything. I can clearly see there is no data dependency between other entities. This is something that I can trivially chunk in whatever way I want. So it also helps with that aspect. The point I'm trying to make is that DoD is not just about performance, but also keeping things flat and data-oriented really provides many side benefits that you might end up not having if you use OOP. Okay, I'm running low on time, so I'm going to skip a few things, or rather go quite fast. So the second thing that we're going to do here is basically get rid of that enum class. And the way we do this is quite easy. We remove the sort of like flag or choice from the state of the entities, and we do something that we've done before. We use more containers. So instead of storing particles, we're going to store smoke particles and fire particles. Instead of storing emitters, we're going to store smoke emitters and fire emitters. So the point here is, if you have branching in your loops, instead of branching during the loop, try to group the data beforehand and lift it to have multiple containers. And this ensures that when you're looping, you don't have the branch there anymore, and you already have more, organization of the data to begin with. Seems counterintuitive, but this helps, keep track of everything that you have and reduce branching in tight loops. So if we do this in terms of performance improvements, it's not that great. We just have like almost 6% decrease. It's a consistent decrease. But this is not the case, this is not the kind of application where this will show up, because again, the bottleneck is the update of the particles. This was just when we create and destroy particles. But if your application has a very hot loop where you're branching within that hot loop, this sort of transformation can make a much bigger difference than what you see here. Not pictured again, we have a 12% improvement in rendering performance, because again, GPUs like when things are grouped together. If I can tell the GPU, hey, these are all smoke particles and these are all fire particles, and I can bind the textures beforehand, then it's going to be easy for the GPU to draw them. So again, DoD closely aligns with what GPUs really want. Okay, last thing I want to show you is different kind of mindset, which is instead of storing objects as objects into an array, so an array of structures, there is this idea of SOA, structure of arrays, which changes the data layout that you have in your program. And again, running low on time, so I'm going to try to give you the most important tidbits of information, but then feel free to reach out or talk to me, and we're going to dive into the details later. But basically, instead of having a particle like this, we're going to perform this transformation, where we're not going to care about an individual particle anymore. We're going to care about a collection of particles. And instead of having fields individual to each particle, each field is going to be a collection of all the positions, all the velocities, all the accelerations, and so on. So graphically speaking, this is what we had before. Each particle was just an object with its associated data. And now we just have a big table of all the fields. We don't really have an entity anymore. An entity is just the conceptual idea of slicing this array vertically and seeing what's in every slot one to see what that entity is. So we call this, the one on the left, we call it array of structures, and the one on the right, we call it structure of arrays. In AOS, the entities are explicit. Every object is a complete entity. In SOA, they don't really exist. The entity is conceptual. In AOS, you might have padding added by the compiler between fields if there are alignment requirements. Padding seems harmless, but then if you realize that it's taking space in your cache, it means that the more empty bytes you have, the slower your program is going to be. With SOA, you have no internal padding. Every single byte is useful because every vector stores the exact same type, so you don't waste any space in the cache. In AOS, even if you care, for example, even if you care, for example, about a single field in the particle, maybe you care about the position, you still have to load everything nearby because particles are stored contiguously. So when you load the position of particle 2, you will also get some velocity acceleration in the cache line, something from the previous cache line. It really makes it hard to individually use a field without wasting cache space. In SOA, we have what I like to call surgical field loading. If you only care about positions, you're only going to get positions. Nothing else is going to pollute your cache as you work with those fields. AOS can be vectorized, but it's not the ideal layout for SIMD, so the compiler is going to have to do some stuff to make that work. We're going to see an example later. SOA is ideal for vectorization. Because every field data is contiguous, you can easily see how I could take a SIMD register with all 4 positions and then all 4 velocities and perform a vectorized operation. It becomes much, much easier for the compiler to do vectorization on this stuff. And I also want to add, it's also ideal for GPUs. GPUs really like this layout as everything is flat and contiguous. So I'm going to skip through the implementation. I think you get the point, and I'm running out of time. I'm just going to replace this with the SOAs. And then here I'm going to do some abstraction to make it a bit less repetitive. The only thing I want to show you is that this becomes quite annoying. If you are creating a particle, now you cannot just push back a particle. You have to push back 9 times on every vector. So in terms of simplicity, we do lose a bit of that with this approach, and I'm going to show you in a bit how we can recover that. Okay, also cleanup and whatever. So once we do this, we get another pretty big improvement. We get around 32.02 decrease in update time, and also 2 times better draw performance, twice as good. And I mentioned that before, the GPU really likes flat contiguous data. But if you think about it, this is not a good use case for SOA. We're already using all the fields. We don't need to use a subset of the fields. So why are we getting this huge boost if, technically speaking, we're still getting the same data in the cache? So I did a bit of digging, and I noticed that if I look at the assembly, both AOS and SOA are using SIMD instructions called fuse, multiply, add, which is an efficient way of performing the sort of integration step that we've seen before. But in the AOS case, because the data is scattered, first the compiler tries to get it together using gather operations. So it takes it from different places and puts them in the same register, then performs the fuse, multiply, add, and then it scatters it back to where it came from. So there is some overhead associated with the fact that the data is laid out in a strided fashion and not allocated continuously. So the SOA avoids that extra overhead, and I think this is the biggest reason why it's much faster. There are other possible factors. Some particles in AOS might end up being on the boundary between 2 cache lines, so the compiler might have to read multiple cache lines to get the work done. Prefetcher usually has harder time if you have strided access. That's much more predictable. And you might have a few extra register pressure because of the gathering and scattering there that needs some extra registers to store those addresses. But I think this explains the performance difference. The last thing I want to talk about is, did we sacrifice simplicity with SOA? And I think we did. The problem is that C++ really has no native support for SOA. Both the language and the standard library are designed around AOS. You can get around some stuff by using lambdas, and it does help with repetition. But can we do better? And I think we can. So I like this. This is concise, easy to understand, and everybody understands the idea of a particle. I don't like this because I have to manually transform the nice idea into SOA. So it would be cool if we had some sort of magic template called SOA, we gave it a struct, and then internally it generated what we've seen before. It basically converts this from AOS to SOA automatically. So if we had this, what could we do with it? What would the API look like? Well, the pushback could look normal. Instead of pushing back into 9 vectors, we could just give this API a particle, and then internally it would scatter it in those 9 vectors. So that's nice. If we wanted to iterate over all the fields, we could have this with all function that, given a lambda expression, it would invoke it with all the fields of every particles at once. So it feels like we are iterating our objects, but internally it's actually fetching the data from multiple vectors. And finally, if we wanted to iterate over a subset of fields, for example, just scale and scale change, and we don't care about the other ones, we could have this with interface that, given function pointers to those fields, will just extract those vectors and invoke the lambda with the fields of every particle. Again, very convenient, but internally uses the SOA layout efficiently. You might think we need reflection for this, but we can do all of this in 17. You can actually implement primitive reflection using C++17. I've actually done this using Boost PFR, which is a library that reflects on aggregates. And I do have an implementation of this in the demo, and you will see the performance is identical to the manual SOA. So effectively, this is a zero-cost abstraction, and we can get it today with C++17. But what can we do in the future? Well, with reflection, we can do more interesting stuff. For example, we could just call with like this, and then reflection could actually look at the names of the parameter. And by looking at the names of the parameters, it could automatically extract the fields from the particle. C++26 reflection is going to be powerful, a bit scary, but you better get used to it because people are going to start doing stuff like this. So even the names of things are going to be meaningful for the semantics of the program. There is a very good talk as it began from Barry called Practical Reflection. It's not out yet, but when it comes out, I would advise you to take a look at it. He exactly deals with this problem of converting AOS to SOA, and he shows you how you can use C++26 for that and implement this API. Okay, just a few final touches. I'm gonna be, maybe 5 minutes late, but I wanna mention this is important. DoD doesn't mean using SOA by default. It means designing your architecture with a focus on data layout. So you don't immediately jump to SOA. You let the access pattern choose the layout. You have to think about, in my problem that I'm trying to solve, which fields I'm going to access frequently together, which fields are more cold, what is the SIM delay size. So think about your platforms, your access pattern, and that is going to choose the layout for you, not the other way around. And if you do so, you're going to get maximum utilization of the hardware. And I also feel like many people think that abstractions are going to be detrimental to that. I think it's the other way around. We have seen how you can convert AOS to SOA, and you can have similar ideas to switch between layouts at compile time. And that helps you experiment and see how certain layouts end up working out in different situations. And as we've seen, C++26 reflection will make this easier. At the same time, I feel like DoD is not always the answer. OP is not bad. I just feel like OP is often applied at the wrong level of granularity. If you apply it at a coarse level, then it does make a lot of sense and makes things easier. Example, you could have a particle manager OP interface and API that internally uses DoD, and that gives you the best of both worlds. So the problem is not using OP, it's using OP for the particle. And if you do this, you can have multiple strategies with virtual polymorphism. It doesn't matter, again, it's just one function call, not 1 million virtual function calls. So it gives you that nice straightforward polymorphism without any extra, overhead. In teams, OP helps if you have boundaries with APIs and private and public invariants. It does help correctness and collaboration in parallel on the same code base. So what I suggest is a hybrid approach. OP is the shell, and DoD is the engine. Okay, so I'm not going to bother much with this, just a few things. If performance is a requirement, it should be part of your design. It's not premature optimization. Flatten and shrink your data. Computers like that. Group data by usage instead of Boolean flags and enums inside your types. Have more containers. Group it beforehand. And SOA might be useful if you need bulk processing. In general, data drives design. Target the machine, not the metaphor. It's not dogma, so use what fits your problem. Modern C++ helps, and pragmatism always wins. So the last message is think data first. Your code will be faster and simpler. And you can find everything regarding this demo, code, slides, and so on, and some links regarding myself and my business here using this QR code or this link. And I'm a bit late, sorry about that, but I'll be happy to take questions right now. Okay, so okay, so let me try to summarize that for the recording. You're saying that the allocation scheme that I shown might be changed in such a way that even by using allocations in a more, let's say, clever way, might be faster. So I consider using also polymorphic allogators, you know, about SADPMR, for example, where you can fetch memory from a same region. The problem with that is as soon as you start creating and destroying entities over time, you're still going to get memory diffusion. So yes, they're going to be coming from the same arena, from the same pool, but they will not be in order anymore because you're continuously recycling and creating stuff. So even with that aspect, you end up having cache misses. It's going to be a bit better, but it will not match the performance of DoD. So we can discuss that later, but I suspect it's going to be an improvement, but not as good as the manual way of doing so, if I'm getting your question, but I'm happy to talk about later. Yeah, yes. I tried using a different language for this sort of purpose. No, I specifically focus on C++. I think that other languages like Python, which are interpreted, are going to have an inherent extra overhead because of that. I do see the value of using languages like Python, let's say like glue code. For example, most of the AI stuff or machine learning is nicely laid out in Python, and internally those kernels, those things that are doing the heavy lifting, use something like this. They would lay out the data in such a way that it's nice for the GPU, data-oriented. So again, like the hybrid approach with OP and DoD, I feel like there's a hybrid approach between higher level languages and low level languages that gets the best of the both worlds. Cool. Thank you so much, everybody. Happy to chat later. Cheers.